Hello and welcome to Bits and Pieces, lecture number 2, bit operators. Last time we took a look on how binary worked, how hexadecimal things worked and so on, and we also took a look on the relation between bits and bytes. This time we're going to take a look how we can use these further. We didn't really use the bits too much, we just saw how they worked and so on, but not really why we would even bother about them. But today we're going to operate on them, we're going to use bit operators and see how that works. So, let's get started. But before we can do so, I'm just going to write a simple class here. So public class bit operator test. I think that's a good name. We're just going to test things anyways. And just a main here. Public static void main. Like this. Okay. So when I have this here, what I want to do is the following. It might not make a lot of sense at first, and that's actually the point. So what I want to do, you'll see in just a second. Byte B1, so I want one byte here to be 21. I want another byte to be 28, okay? And then I want a result here. And when I calculate this result, what I want to do is use a bitwise operator. We'll take a closer look on that in just a second, but what I'm going to do is do byte 1 and byte 2. This is AND. Don't mix it up with the logical AND, which looks like, well, if you want to do an if statement with like true and false, then you have two of them, AND there and AND there. But when you do it with bits, then you just use one. Okay? We'll see in a minute or so exactly what's going on here. And then I just want to print out the result. So print line like so, and I print the result out like that. Okay, this is not going to make any sense, and that's sort of the idea, which might sound a bit weird, but we'll see in just a second. Oops. So there you go. I run it. If it compiles it all. Hold on. There we go. Took some time. And what's going on? There you go, 20. Okay. Makes sense? No. So we have 21 and 28, and that equals 20. That doesn't make any sense at all. But let's take a look. This is about bit operators. This is a bit operator. Let's convert these to binary and take a closer look what's happening. Maybe it makes more sense then. So 21, what's that in binary? Well, I'm just going to add some comments here to help me along the way. Okay, the highest multiple of 2 that is still smaller than 21. Well, we have 1, we have 2, we have 4, 8, 16, 32. 32 is too big, 16 is fine. So we have 116 there. If we take, for instance, 21 minus 16, because we used 116, then we will have 5 left. Okay, 5. The largest multiple, what do we have? 1, 2, 4, 8. Okay, 8 is too big, we use 4. Here, there. And then we will just have a 1 left, like so. So then I can just add a 1 there. And what we'll get now is, of course, 1 bit there, 1 bit for the 4, and 1 for the 1. So what we will get in the end is 1, 0, 1, 0, 1. So that's the 1 there. The 2 we don't have. We have the 4. We don't have the 8, and we do have the 16. But well, I can add the 3 remaining bits there in the front. Add these ones there, and just proceed them with 0b there to tell that it's binary. Okay. So now we have that one in binary. Let's do the same thing for the other one. Okay. What do we have here? Well, 32 is still too big, so the biggest one that we do have is 1 bit, that is 16. If we take 28 minus 16, we do get 12. So we have 12 left here to distribute. So what do we have there? Well, the next one that comes is obviously 8, so we just use that one. And then we're going to have 4 left, and therefore we get a 4. So we'll split this up in these 3 bits here. So we have 16, 8, and 4, and that will give us the 1, 1, 1, 0, 0. So we have the 1 and 2 there empty, and then I just add 3 zeros to the start. We don't have to add those 3 zeros, but just to mark that a byte has 8 bits in total. So preceding zeros do not do anything really, but just to make sure that we have 8. Okay, right. Okay, that's the first step. Now we have it in binary. It still don't make any sense. Why would we get 20? Well, what we want to do now is just tell it, well, can't you just print this out in binary? So bit operators don't make too much sense when we work with them in base 10, because if I had 21 and 28, what's happening now? Let's see. Kind of find symbol integer. When we had 21 and 28, we got 20. And if we're going to take a look on this in binary, I'm just going to copy this, then it's actually going to make perfect sense. 1, 2, 3, 4, right? I lost a 1 there, sorry. There you go. So that's the same thing there with 3 zeros in this beginning. And I'm just going to move them here so we can take a closer look. Okay, now we have everything in binary. So instead of having 20 and 28 equals 20, what we have now is this sequence here, and that sequence there, you know, the and there, and we get this sequence. And now it actually starts to make sense. Look at this. We have a 1 in the result there, because we have a 1 in the result there and there. Here we have a 1 in the result, because we have a 1 in the result there and there. Everywhere else we have zeros. Here we have zeros, because we have a 0, 0. Here we have a 0, since we have 0 and 1. And here we have 1 and 0, and that also gives us 0 in the end. So what the bitwise operator AND does is give us a 1 in the result if we have a 1 in both the values at that specific bit. So the reason so why did we get 20 when we did 21 and 28? Well, that's just what these represent. So this is 21 in binary, this is 28 in binary, and if we put them together and compare the bits here, we sort of happens to get 20. It doesn't matter anything. It doesn't matter to us that we do get 20, because at the moment we don't work with them as base 10s or anything. We just work with them as individual bits, and then we happen to get 20 if we want to translate that to base 10. So that's why we got 21 and 28 going to 28. That doesn't seem to make any sense, but if we take a closer look on the individual bits, then we see that this AND thingy do make sense, and what it does is just give us a 1 in the result if we have a 1 in both the bits of the values, like so. But what can we use this for? Well, we can use this for multiple things, of course, and some of them might require other bit operators as well. We'll see them later on. We have a 4 bit operators to take a look on, and then we have something called bit shifts as well, and all of those things will be covered in this lecture. So we'll improve this example as we go along. And I want to create a person class here. I don't know exactly what we're going to use it for real usage. What I'm going to have it for is, well, basically testing, as an example. And what I want to do is store all the data that we do have there in one byte there. And why would we do that? Well, we could do a lot of different data in different variables and so on, but if we for some reason happen to have this restriction, I'm going to show you how you can do this with just that 1 byte. Maybe, for instance, this is just an example. Take Minecraft, for instance. When we have a block, we have a metadata. How much can we store there? Can we store an infinite amount in the metadata? No, we cannot. We can store 4 bits. How can we yield as much as possible from these 4 bits? Well, we can use bit operators to sort of modify the bits individually. So that's exactly what we're going to do now. But we're going to use a full byte, that's 8 bits, and we won't really have a proper reason why we would do this at the very moment. I want to, so you can do the following. So when you create it all, I want you to be able to just give it the data and then we store it like so. But the important parts are the followings. I want to be able to check if this person here is an adult or not. Is adult like so. So what is that? Well, that's a Boolean value. A Boolean value is either true or false. So that's like maybe this bit here. If that's 1, then maybe it's a adult, maybe it's a child, otherwise, you know. But a Boolean, when you save it normally, it takes up 8 bits, because that's the smallest thing we can allocate. It's 1 byte. So we could have 1 byte for a boolean, but we can just use 1 bit from the data here. And how do we do that? How do we use the data to define and see if 1 bit has been set to 1, for instance? Well, what we can do is the following. Obviously, what we're going to use is the bitwise operator AND, because that's what is the one I just showed. Okay, so data. So that's the data I have. So now I'm going to do AND here, 0 B, just to tell it that this is a binary. And just for completeness, like I've done before, I'm going to add all the bits. So 1, 2, 3, 4, 5, 6, 7, and then a 1 in the end. Okay, so what am I doing now? Well, what I'm doing is doing an AND here between this thing. I'm using that as something called a mask. So what I'm going to do is get the values just at this specific location. Why is that the case? Well, think about it. If we have something here in the data, and then we AND that together with this thing here, what we will get in the end is only the ones that we have in both the data and the mask. And since the mask only has a 1 here, we can never get any 1s at these locations, because we have 0 there in one of them, and therefore even if we have 1s in the data, they won't get through. However, if we have a 1 at the lowest position here, the least significant bit in the data as well, then we'll get a 1 as the result. If we have a 0 in that location for the data, then we'll get a 0 in the result. So basically what we'll get is the value from data here at this specific bit. Because if it's 0, then we will get 0 and 1, and therefore we get 0 in the end anyways. And if we have a 1, then we will get 1 and 1, and we get 1 in the result. But for all other bits, we will always get a 0 due to the fact that the mask itself has a tons of zeros there. If we had 1s there, they will come through as well. So if we wanted like just 2 bits to come through this mask AND thingy here, then we could do it like that. Then we will get the values of that specific location out from this AND here, the binary we get in the end, or well, the byte there. And what do we want to do with this? Well, what we want to do here is check that this is, well, we could check it if it's equals to 1. If we check that it's equal to 1, what we get here is well, if we have that bit, then it's equal to 1, and then we want to return true, because then it's an adult, otherwise a child. But it would be sort of the same thing to do it's not equals to 0, right? So we check that, is it a child? Okay, then we return the opposite. We'll see in just a second why it's sort of better to do it this way, like that. So what I'm going to do now is do public boolean is boring. So I will have another method here, okay? Of course I can't use the same bit. That's the one I just used. I'm going to store if it's an adult using that bit. So what I'm going to do here is the same thing, but with another bit as being 1. So data and 0b 1 2 3 4 5 6 1 0, like so. So now I'm using that bit instead, and that means that I will get the result from that bit, because that's the only one that is 1, and then when I AND that together there, then I will get the result there. However, I can't just do equals 1 here, because that's not what I'm going to get. I'm never going to get a 1. What I'm going to get is 10, right? Because, well, if I have a 1 at that bit, at this bit here, what I get is not just a 1. I get a 0, 0, 0, 0, 0, 0, 1, 0, like so. So I would have to check it against that or against 2. And then if I use this bit here as well, then I would have to check it against 6, and so on. So what we might want to do is just check, well, if it's not equal to 0, and that's exactly why I did so up there. So we can check it individually, depending on what we're expecting to get, but it's much easier to always just check it's not equals to 0. Like so. Okay, so there we go, and then I want the last one. I want to have a score for this person. So public and get score, like that. Return. And what do I want to do this time? Well, the score I want to return is, well, I'm not going to return it as big as an int. That's impossible. I'm just writing it out there because it doesn't really matter. But what I have here is I'm going to define the score between 0 and 7. The reason is because 7 is the greatest number you can have with 3 bits. Maybe I wanted to use 4 bits, then I would have between 0 and 15. But I think 3 bits are just fine for this thing here. So how do I do this? Well, what I want to do is do data and then do the same thing that we've done before. 0, B, 0, 0, 0, and then 1, 1, 1, 0, 0. So what we do here is we have zeros here for the two adult and is boring ones, like so. And then what we have here is 3 ones here. Those are going to indicate the score, so we only get the score there, the score that we have at that position. So even if we have things here, they are not going to be sent through, they are not going to bother us. Even if we have things here, they are not going to bother us. And that's exactly the same thing with these is boring ones here. It doesn't matter if it's an adult or not when we check if it's boring or not, because they are operating on completely different bits there. If we would only do data is not equals to 0, then it would of course be boring as soon as it would be something. If it would be an adult, then it would be automatically boring. If it had a score, it would be automatically boring. But what we want to do is of course just get the data there, and we're doing the same thing here. However, when we do this, we will get something like, I don't know, 0B11100. We have 2 zeros here. They will be there. So this is going to be 4 times as big, 2 times for each step we take here. So what I'm going to do is just divide it by 4. So it gets 4 times smaller, so we get it properly. Now we'll get it between 0 and 7. This is not the proper way of doing it, but we'll take a look on how to do it properly after the break. So for now, we're just going to divide by 4 here. Okay, that's pretty much it for that. Let's compile it. Yes. What happened now? I think, what? Okay. Silly Dr. Java did something wrong. Here you go. It tries to save it as the other name there for some reason. I don't know why. So it saves the thing on the other one. So you should be called person. Come on. Some issues here, sorry about that. There we go, and now everything here got messed up, but that doesn't matter. I didn't intend to use those things anyways. Public bit operator test, public static void main string. So what happened was that it suggested that I would use the bit operator test name even for the person class, so all of a sudden I started to save it over each other, and everything got messed up. I don't know why it suggested that as the name, but sorry about that. So what I want to do now is have a person here. I'm going to call that Bob, a new person, and I'm going to give it some information here. Tell it that it's a byte, and then do 0, 0, 4 zeros, I think, yeah, and then 1, 1, 0, 1, like that. Okay. And then what I want to do is print some information out depending on the info we have. For instance, it's boring. Bob.is boring. Like that. Oops. Silly me. Oh right, that was because I screwed up. There were no class. Yeah. Silly mistake. There you go. So now we can print that out depending on if Bob is boring or not. And if we run here, we'll see is boring is false. The person is not boring because this bit here is a 0. If I change that to a 1, it's now going to be boring. Like that. Is boring true. And as you can see, it won't matter if we have a 0 there or not, because we're just going to work with one specific bit there. We're just getting the value there. We don't care about anything else there. But it's annoying to just do this all the time, so what I'm going to do is head over to person here and add a method that can print out the data for us. So public void print info, like so. This person is a, and then we can add, if it's boring, then we want to add boring, otherwise we can add fun, and then we can add space there, and then depending on if it, oops, a space there, and depending on if it's an adult or not, we can add if it's an adult or a child. Adult, like that. Was that correct? Yeah. And then if that's the case, then we want it to say adult, otherwise child. And then finally we want to add a score here. I don't know what the score tells us, what score it is, but we're going to have the score here. Okay. So now I store a score that has 3 bits here. It just uses 3 bits, like so. I store and 2 Boolean values in 1 byte, and I still have 3 bits here to go. So all of a sudden I'll put everything there much more compact, and then we can just do bob.printinfo. So why would we even do something like this? Why would we put everything there in just 1 byte? Well, we've seen oh, it might be a good idea to actually print this out. Like so. Okay. Let's run it. There you go. So this person is a boring child with a score of 3. I'm just going to set that to 0. So it's a fun child. But why would we even do this? Well, as I compared it to the metadata that we had in Minecraft, there we just have half a byte, we have 4 bits. So now, maybe we just can store everything in 1 byte, maybe we can't store it in anything more. What if we had these 2 methods? I'm not going to use these 2 methods really, but what I'm going to do is give them as an example. Maybe we want to synchronize this data between 2 servers, maybe between 2 clients, maybe we want to save it. Well, then we can return all the data in just 1 byte. And then we can do the opposite, set data from sync. So maybe it has been synchronized, we want to set default data here, then we can just do so, byte data. Like so. So maybe we would want to do something like this. Now it's very easy. Now we just have to synchronize 1 single byte, not 1 byte for the score, 1 byte for the Boolean is boring, and 1 byte for the is adult one. We don't have to do that. But what we could do if we wanted to would be to have 1 Boolean for is adult, 1 Boolean for is boring, 1 byte for the get score here, and then when we synchronize it, we would compress everything to 1 byte and then send it, and then when we got it back we would unpack it again. And that's totally possible, but we don't know enough about bit operators yet to be able to do so. So that's why it's set up like this. Okay, so the next step is another operator, another bit operator. So we had AND, so you can probably guess a name that we might have. So what I'm going to do is define 2 new bytes here. We're just going to hijack this bit operator test class here. So 0b 01010101 like that. And then I want to have b2 here 0b and then 01110010 like so. And I don't have a clue of what these are in base 10. That doesn't matter. We don't have these bits here because they are represented as something in base 10. And then what I want to do is use the OR one. So we have used the AND one, and now I want to use the OR one. And I'm going to do it like this. B1 or B2. So once again, don't confuse it with the OR one for logic when we have true or. Well, we have 2 vertical pipes there, like so. That's not the same. Now we just have 1. And always when we use, well, these bit operators, they are actually applied as integers, so that's why I have to convert it back to a byte when we're done. So it sees these 2 as integers, and then it does the bit operator before we get the result there. And now I'm just going to print it out, and then we can take a look on what it actually does. You might be able to guess it already. Okay. Then we run it, and this is the result. I'm just going to copy that, like we did before. How many do I have? 1, 2, 3, 4, 5, 6, 7. Let's add a 0 there. Move it like so, just to take a look, obviously. So now we can see we have quite a lot of 1s here. The reason is, when we do a OR, what we get here is a 1 if we have a 1 in any of these. So here we have 1, that's cool. Here we have well, 2 ones, that's even better. Well, it doesn't really matter really. We get a 1 there anyways. Here we just have 2 zeros, therefore we get a 0 in the result. Here we have a 1 and a 0, we get a 1, a 0 and a 1, we get a 1, and finally a 1 and a 0, we also get a 1. So as soon as we have a 1 in any of these two, then we're going to get a 1 in the result. That's why it's called OR. We have a 1 in this one, or we do have a 1 in that one, and therefore we get a 1 in the result. So there we go, we have the bit operator OR, and we also had the bit operator AND earlier. We'll see more in a bit, but we're going to continue with this example. Okay, what if we want a method here called grow up? Maybe we want a child to be able to grow up. There's a reason why I wanted Bob here in the end to be a fun child, so we can make him grow up, but also to make him boring as well. But most of that in a bit. So what I want to do here is use the obviously the bitwise operator OR. That's why I would use this as an example just after we saw that one. So grow up like that. Okay. Data equals data. Okay, what do I want to do here? Well, if I maybe that's not what I want to do. What I want to do is obviously set it like this, right? Well, if you think that's the case, then well, you might have to rethink, because if we do it like this, then what is going to happen is we're going to lose the boring state. Maybe we had a lot of information already. The person might have been a child, yeah, so it might have been 0 there, but it might have been like 1 there and 1 there or something like that. So by us setting everything like this, that would overwrite everything and indeed make it grow up, but it will also always become fun, and it would always lose its score because all of these would be 0. So that's not a good idea. But if we use data here and do an OR and then add that, what do we get now? Well, what we get is simply, if we had a 1 here before, we're going to keep it, right? Because in the result is going to depend on the 2 values we have here in the bitwise OR, and if we had a 1 in any of those, then we will have a 1 in the result. So we have all the old ones will be kept and stored in data here, but we will also get a 1 in the result on the last bit, on the least significant bit. So that will always make sure that the person grows up, because we set a bit at the least significant one, which is indicating if it is an adult. But since we're using OR here, we'll also get all the ones that we already had. That means that if the person were boring already, we won't lose that information. If the person had some score, we won't lose that information either. And that's pretty much what we want to do. But you know, operators, coders, lazy, you know, that sort of things. So we can just do OR equals to like that. So what I'm going to do here is take the data and set it to the data or this part here, which makes sure that we keep all the information that we have, apart from that we add a 1 as the last bit. Even if that bit was true already, we will also get a 1 there in the end anyways. So that's how we do the grow up. And then I want to do another thing here for turn boring, public void turn boring like so. Oops. And then what I want to do is the same thing. So data or equals to, but this time I want to use 0b 1 2 3 4 5 6 and then 10 like that. So now it's going to always make sure to add a bit or 1 as the bit there at that position, just because we use data or this value here like that. Or if we wanted to, what we could do would be something like this: public void really grow up, or well, rather grow up for real, because when you grow up you usually, well, it gets a bit boring. So what we could have is like 1 2 3 4 5 6 like that. So what it would do now is would make sure that we get a bit at that position and that position, which would make sure that the person turned boring and grew up at the same time. But you know, hopefully that's not the case, so let's remove that. So as you can see, we can make sure that we set a individual bit there, like so. And then we can simply use that if we go back to the test here. I'm going to use the old Bob here. So what do I want to do? Well, I printed out the information, so now it might be a good idea to tell Bob to grow up. and bob.printinfo, so we get the information of Bob there. Then we can tell Bob to turn boring, and then bob.printinfo again, like that. Okay, so let's take a look. What we have now is this person is a fun child with a score of 3. This person is a fun adult with a score of 3. This person is a boring adult with a score of 3. So as we can see, it's not changing any other values than the ones we asked for, just because we still keep that information. However, if we wouldn't do it properly, for instance, we might want to just set it when we grow up, we want to just set that bit there, then we will see that we will lose all the information when we do so. So now if I run it, we will have this person is a fun child with a score of 3, this person is a fun adult with a score of 0. So we just lost the score. We also lost the information if it was boring or not, but now it happened to be fun, and therefore that didn't change. So by using OR here, we will set that bit, but we will also keep all the ones that we already had, like so. So that's OR for you. Now we're going to take a look on something we do not have when it comes to logical operators, and that's something called XOR. More to that when I've typed this example. So we have B1 there, and I want to use 0B 001 00011, like so, and then byte B2, and that should be 0B 01 000110, like so. So something else there, and then I'm going to do something similar here. So just byte result equals byte, like that, B1 XOR B2, like that. Okay, so far so good, right? And then print it out. Integer dot to binary string, like that, and then we get a result. Okay, sweet. Let's see what the result is, like always, and then I can run it, and we get this thing here. Let's put it here. I think it's missing 1 0, so let's add that 0 in the beginning and move this over here and take a look. Okay, so what do we have? Well, this is pretty much like OR, isn't it? 0 1, you know, 1 1 0 1, you know, 1 0, that's 1 as well. 1 0, that's 1. Everything seems to look like OR. 0 0, that's 0. Oh right, 1 1, that turns into 0. That's odd. Well, XOR, as it's called, exclusive OR, means that, well, the OR is exclusive. We can't have two of the ones here. We can only have one at a time. So what we have here is 0 1. That's fine. We have a 1. When we have 0 0, then we do only get 0. And when we have 1 1, we also do get 0. So for it to be the 1 in the result, we will have to have difference. Well, a difference between the two bits. We need a 1 in one of them and a 0 in the other. And as you can see, we're using this arrow here for XOR. So if you try to do the power off and use that one, you might have realized, oh right, I get something very weird results. Maybe we wanted to have x in the square of x, and you tried something like that. Well, what you actually did was the bits of x you did XOR with of the bits of 2, and probably got a very weird result when you did so. If you actually want to do it like the square of x, then you would do x2 like that, method pow for power. Or if you just have the square and nothing more advanced, then you can just do x times x like that. So this is not power off. This is XOR. So we take an XOR between the first value and the second value, like so, and therefore we'll get ones where we had a 1 in any of the bits here, but the values, sorry, but we won't get a 1 if we have it in both, like that. And we're going to use this as well, of course. So let's head back to person here. I can move that down. Okay, so for this example, I'm going to add one more thing. I'm going to add something called is ready. I'm not entirely sure what that is going to define, like ready for what, but in the end, this is just an example. So public boolean is ready. So how do we want to do this? Well, we've seen this before. Return data and 0 B0 1, and then 1 2 3 4 5 6, like so. Okay. and that should not be equal to 0. Okay, alright. So what I do here is just the same thing as before. That one is used by the adult, that's used by the boring part. I actually added one too many zeros here. Right? 2, 4. No, I haven't. Sorry. I just added the 1 in the wrong location. There you go. So what we have here is that one is the adult one, that is the boring one, and these are the ones for the score, and then that one is the one we use. So we still have 2 bits left that we can use there for something else. So that's just a ready state there, and I'm just going to use it down here when we print out the information. So string plus equals, so we can add a period there, and then afterwards I want to do if is ready, then str dot plus equals to ready for action. I don't know ready for what action, but apparently this person is ready for action, like so. So there we go. And what we want to do now is, well, what do we want to do? Well, I want a method that is going to change the ready state. So if you were ready, then you're not ready anymore. If you were not ready, then you will be ready all of a sudden. So public void change ready state, or flip ready state, or whatever, like so. Okay, so what is this going to do? Well, if we had a bit on one location, on this location here, then we want that to become a 0 if we had a 1, or a 1 if we had a 0. And what we can do is the following. We've just gone through XOR, so obviously we're going to use that. So data equals data XOR 0B 001 1 2 3 4 5. Right? 1 2 3 4 5. Yes, like so. So what's going to happen here? Well, basically, if we have a 0 here, anywhere else than the 1, what we have is a 0. And if we have a 0 in data at that specific location, then the result is going to be 0, right? We have 0 and 0, well, 0 XOR 0, and therefore that's going to turn into 0. If we go back here, we have 0, 0, that's always 0, right? Okay. If we have a 0 here, but we have a 1 in the data, what do we get? Well, we have a 0 and a 1, then we will get a 1 in the end. So the result is just going to be the same as before. We're not going to change it. However, if we have a 1 here, what's going to happen? Well, if we have a 0 in the data, then we're going to have data XOR 1 there. So the 0 XOR 1, that's 1. If we take a look, that's just if we had like a 0 there and a 1 there. So we actually get a 1 in the result. Well, a 1 there and a 0 there, sorry. So we get a 1 there in the result. So that's actually going to set it. But if we take a look, what's going to happen if we already had that bit? Well, if we already had a bit as 1 at that specific location in data here, then we can get 1 XOR 1. And if we have 1 in both, it's going to turn into 0. So what we are doing here actually is, where we have a 1 here, we could have that in multiple locations like that. We can, well, maybe we can control if it's boring or not in the same time. So what we do here is, all the time where we have 0 in this mask, what we're going to do is just keep the old value of data. Because if we have a 0 here, what's going to happen with the XOR is that it's going to take its value directly from here. However, if we have a 1 here, then we're going to flip that value. Yes, because if we find a 0 there, we're going to do 0 XOR 1, that's going to give us a 1. But if we have a 1 there, then we're going to do a 1 XOR 1, which is going to give us a 0. But we don't want to control that one. And of course, operator laziness, we can do it like that. There we go. Right, so now it's just a matter of running this in the correct class, like that. There you go. Okay, sorry. We might want to do something as well with that. So what we want to do is simply do a loop here. That's what I'm going to do. I'm going to loop through 4 times. And then what I want to do now is do bob dot change ready state, and then bob dot print info, like that. So I just go through 4 times. Each time I go through the loop, I'm going to change the ready state and print out the information. So let's compile and run. This time it's going to work better, and what we'll get here is the following. So we have this person is a boring adult with a score of 3 and ready for action. Then that ready for action is going to set to 0 or to false, and therefore we'll print it out without the ready for action. Then we're going to set it to true again, and get ready for action here, and then we will lose that again like so. So every second time it's going to be ready for action when we do it here. Yes, because what we do is do bob.change ready state. Oops, there we go. Bob.change ready state, and what that is going to do is that it's going to use XOR here to swap the data, and we only make sure that we swap the data in that specific location. It's not going to swap the whole thing. If we would do that, then everything would be messed up. If we take a look, we could add one there as well, and now if we ran it, we would see that it would also affect if the person would be boring or not. So now if we run it, we will see that here we have a boring adult with a score of 3, we have a fun adult with a score of 3 ready for action, and then it turns boring again, then it turns fun and it's ready for action, and then it's boring adult with a score of 3. But don't think that, alright, now we've done so it's ready for action when it's fun, or vice versa. That's not the case, because if we do it like this, if we remove the boring part here, so it's not boring, then it's going to be boring when we start this process, and that's going to make sure that it's boring when it's ready for action and fun when it's not. So these are not connected in any way. We just flip them at the same time. That doesn't mean that they are always going to have the same values compared to each other. It just means that, well, when we do this flip, then we flip the bits at these 2 specific locations, and that's going to do that impact that they both will flip, but we don't know what values they had in the beginning, so they might flip in opposite directions. That's totally possible. So it might be a bad idea to do it like this if you want them to be the same. If you wanted to, then we could just say, alright, you can never be boring. Oh, there we go. You can never be boring if you're ready for action, for instance. We just check if is ready, then return true, for instance. That would make sure that would be the case. So we check the is ready state, and then if you are ready, then you're always, or well, sorry, the opposite, return false, like that. But you know, that's just a little side note there. So there we go. Now we have used 3 of the 4 different bit operators. We haven't taken a look on bit shifts yet, but as you might expect, those things will be covered after the break. So after the break, we will take a look at the 4th and last bitwise operator and take a look on the bit shifts and see what we can do with them. We will improve the person example, but we'll also take a look on another example later on to finish that off in the end. But like I said, that's after the break. I'll see you in about 15 minutes.